We actually had a lot of students from De College, Foothill College, and this is before I got there, but George Cooper, who's our boss, he's the head principal investigator at NASA. He's a civil servant, he's an actual NASA scientist. He actually would have a lot of community college students work with him because you're close by. You can go to school during the morning and head on over to Ames in the afternoon. So this will be a theme I'll bring up in a little bit, but a lot of labs do rely on undergraduates, people that are starting out in science and want to explore that. And so these are the students. These are previous students here, and these are some of our current students in the lab. Mastawal actually is now a researcher with us. She got her Bachelor's of Science in Biochemistry, and in the lab, at school, when they came to the lab as a bachelor's, as an undergraduate, but has stayed on now as a researcher. And she's quite the researcher. She's really helped us out a lot. So that's just a little bit about our lab. We're not a big lab. So actually, I did not move into science. I wasn't interested in science in terms as a career, as my first love. This is some old pictures. My first love was music, jazz. When I was in high school, even before, I started picking up the horn, playing it, and I loved it so much that I pursued jazz. And even after high school, when I graduated, I went to move to the Bay Area. I didn't even go to college, playing jazz. But I was serious about music. In fact, I studied with this gentleman down here. His name is Joe Henderson. He passed away, but he was quite the Grammy Award-winning musician. He lived up here in San Francisco. And I would go to his house once a week and study with him and learn about jazz improvisation. So I was serious about what I did. It's just that I didn't go to college, and I liked music. I did that for a few years, and then I also played Latin percussion and moved in, toured with some bands within California, nothing big, but to see what it's like to make it as a professional musician. It was hard. Didn't make much money. And at some point I realized, am I going to keep doing this, or maybe I might want to think about something else? And I'd always liked the idea of science. My family would always take us to museums as a kid, and I thought, science is something, it's got some creativity in it, but it's also something that's a little more respectable in terms of making a living. And maybe easier is what I thought. So when I decided to go back to, go to school, go to college, I obviously wasn't ready for the 4-year university. I never even took the SATs in high school because I wanted to, just wanted to play music, so I didn't even do that. So I couldn't even go right into a 4-year university. So I started at Cosumnes River College, sister campus, I guess, in the California Community College system in Sacramento. And that was my entrance into taking classes and figuring out what I wanted to do. I still did not know what I wanted to do, but it was this program right here. I happened to be enrolled in a science course, and one of the instructors in the program, one of my biology instructors actually was a faculty mentor in the MESA program. And you guys have the MESA program here, right? MESA. How many people are in the MESA program or MESA program? Raise your hand. Not too many people? Okay, all right. Maybe it's gone down in enrollment, but this program was huge for me. You guys have the STEM Center, so you have something probably better. This is actually where I got to meet people and faculty who helped me identify actually what my major really probably should be. I came in as a biology major because I thought that was something that might be easy, and I liked, as you'll see in a second, why I picked biology. But when I was taking biology classes, I'd always ask questions, in the biology instructor that I mentioned. One day he said, Andro, you're always asking questions that have a chemistry basis. Are you sure you don't want to go into chemistry? And I thought about it, I said, well, no way. And here's one of the reasons why. It's because I looked at all the science prerequisites, and to pursue chemistry, you had to have all of this stuff, meaning so you got a semester of that, semester of pre-calculus, calc 1, 2, 3, and then differential equations, just for a chemistry degree. So many different courses, and I knew where I was because I was solid at the Algebra 2 level. So I was very, very, very good at Algebra 2, so I was going to start in trigonometry. And that was daunting for me. I definitely thought, well, gosh, biology, I don't have to go that far. I could even take calculus that was maybe it's not watered down, but it's the 2-semester calculus. So this was daunting to me, but the lure of the chemistry, the idea of pursuing chemistry was definitely strong enough to make me consider it. And something came to mind. I realized that however anxiety-inducing chemistry was, and these, or not chemistry, but the math courses, I realized that I had some skills already built up. As a musician, and this is an easy piece of music, but often, how many people have played music now, or have played music in the past? Yeah, so you know that new sheet of music is put in front of you, and the first thing you think is, oh my God, I'm never gonna do it. This is gonna take forever to learn. But you know, a little bit at a time, you slow down, take it measure by measure, and you practice, and you practice, and you practice. And that persistence and perseverance, slowly, whether it's a month, longer, you learn the piece of music. Well, that's the same exact thing you need to do, or I needed to do in terms of math. I thought, you know what? I'm just going to continue with that, practice, study hard, a little bit, take a little bit of time and use my resources and see if I can do this. And so, of course, with the support of the MESA program, I realized that, yeah, that was something that I could do and work my way up. What I wanted to do as I continue a little bit about this, I wanted to give you some tidbits of information that might help you out, that helped me out, as I went on through my undergraduate curriculum. So feel free to take mental notes. But I was mentioning to somebody earlier that I think I might be preaching to the choir, so you guys might already know this stuff. I did not, but so if it's redundant to you, you can tune out, but if it's something new that you haven't heard of it before, then definitely tune in. First thing is that when I transferred to the California State University of Sacramento, I knew right away that I had to continue to seek out some STEM support programs. So hopefully when you transfer, find that same type of program like the STEM Center, and most universities have it nowadays. There's something there, find it. In my case, it was the Science Educational Equity program at Sacramento State, very similar to the MESA program, but at the four-year university level. And it's because, this is the main reason why, it's not necessarily just because of tutoring. These programs understand your education is much more than a degree. I mean, it's not just the classroom-based stuff, and you're gonna find out why as I show you in a second here. What you need to do when you transfer, and when I transferred, be part of these programs, is that you need to start thinking immediately about what is it that you want to do. This is a simple question. What do you want to do? You've been asked this since you're a little kid. I wanted to be a fire truck, not a fireman. And so I learned that fire truck and fireman are different. But as you get older, this question becomes a little more pertinent, right, to what you have to do, because you get closer and closer to graduation. How do you know? You know what your major is. The thing is, how do you really know what you want to do? The classroom knowledge is not going to help you. It really isn't. It's going to help you get your degree in terms of what you know in terms of theoretical knowledge and maybe practical knowledge, but it's not going to give you that experience. The only way is to explore. Explore specific careers. Do job shadows, and actually you can do this now. A lot of people think, oh, it's not stuff that you do in high school. In fact, it's better that you do it now. So as soon as you transfer, and even now, start thinking about who has a job that you would love to see yourself, or you can say, I want to be her in 10 years. I want to be him in 10 years. I want to have that job, or maybe not take his or her job, but think about something like that. Well, why don't you contact them? Contact them and say, hey, I want to see what is it that you do, and here's the reason why. It's not necessarily because you want to validate that you think that you like his or her job or you like the career. The most important part is you might realize that you don't like it, and that's actually very important. You may get in, you may have an idea of what you want to do, and then you get there and you're actually pretty surprised that it's not what you thought. And this is why the classroom knowledge does not give you this information. Only something like a job shadow. And why do I say job shadows? First, because they're short. They get you a quick window into time, a quick window into what it is like. And then, most importantly, you have a network. You start building up connections. And that's something I did. I did 6 of those. I did as many as I could do. I went to wildlife biology, to water treatment. I even went out to NASA and visited there towards the end of my career. I was constantly doing job shadows. Now the other thing is that once you identify one that you are actually interested in, think about internships. Do as many of those. Of course, you have to do your classes. But think about these internships. I did two. The first one that I did was with the California Air Resources Board. As soon as I was able to get enough chemistry under my belt, I applied for an internship. And I really realized that I liked lab work more than maybe the idea of going out in the field and doing this. They sample the air in California, they ship it back to labs and monitor it. I liked lab work. Maybe the California Air Resources Board wasn't for me, but I liked being in the lab and using the instruments. So that helped me out. So explore careers. Explore that as you're going, always. Here's the second thing that I did that I hope that you will continue to do. You may already have financial aid when you transfer, you're covered, but continue to apply. As you start to get more advanced in your particular major, you're going to be now able to access discipline-specific scholarship programs. And it's a pot of money that you get if you get into it, but most importantly, it does two things. It puts you in with a special cohort of people that are like-minded in terms of have similar interests, a potential future network, but also you now start building a very specific honors and awards section on your resume. For when you start applying for those internships, it actually helps out. And of course, that age-old adage, success breeds success. That could be the case, whether it's true or not, but it seemed to help out in my case. As soon as I applied for one, actually it was a Hispanic Scholarship Fund. If you don't know about that, if some of you would qualify, apply for that. There's many different types. But then from that, I applied to the ACS, the American Chemical Society Scholar Program. If you can see me, I'm way back there. This was great because now, I didn't realize this was a prestigious scholars program. And of course I had access to people that would help me out and were looking out for me. Do that. All of you in your majors, especially in STEM, will have these discipline-specific scholarship programs. And typically it's when you transfer to a four-year university that you, because you're more advanced, you have to be at a junior level standing. They usually have all these stipulations. So don't forget about those. Because you're in science, even though you may want to go into industry or you know what you want to do, still try out research, undergraduate research, and not necessarily just with faculty, specifically in his or her lab. Try out the research programs, because these are more than just the summer research. They actually have programmatic aspects to it, helping you go through the GRE, learn about how to write up your research and present it besides just at the local department. So I did the Ronald E. McNair Scholars Program, which is funded by the TRIO program at Sac State. It was great, and I did 3 summer research programs. After that, I said, I want to do more, because I liked research in my case. So try it out just once. It may not be for you, but just try it out once. You'll see. Part of that too is, even if you don't do research, start attending national conferences. Couple of things you need to learn about this is that if you are doing research, you get to present your research, but most importantly, you're going to meet people who have interesting jobs and potential ideas to help you stimulate your idea of art. Stimulate your thought about, oh, this might be a good career to pursue. Maybe I can talk to him or her, after. So you come back to your home institution after, you send him or her an email and say, hey, it was great meeting you. I'd love to come out and visit you. Great opportunity to network. I did 6 of those. I did as many as I could. These conferences cost money though. So that's why it's important. It feeds back into finding that STEM support center when you transfer to your 4-year university, because they usually provide funds for you to go. In fact, my first conference I went to, I wasn't even doing research, but the director, Dr. Barena, said, Andro, come on over here. I want you to go to this program. It's called Abercoms. And I said, well, I haven't done anything. She goes, you're going to go. I got money for you, and you're going to go. I'm not going to accept no for an answer. And she says, you got to schedule it with your classes. You got to figure out what to do, but I want you to go. She knew that this was important for us to do. But you get focused in doing your class, your coursework, that you're going to say, well, no, I can't do it. I got tests coming up. No. You need to start doing that. It helps you out. Okay, so how did I do? Well, I graduated from Sacramento State, BS in chemistry, and you might notice a little bit underneath there that I did very well. I persevered, and I did quite well, and I was happy with myself. So I got all A's in my math classes, and I got all A's in my chemistry classes. I think I got an A- in something else, but no, it's whatever level you start off in, as long as you stick with it and do all these other side things that help you understand, you also understand where you want to go and what you want to do after you get your BS degree. In my case, I knew I wanted to go on to graduate work. And so I did the UC San Diego with my PhD in chemistry. And I loved it there and did 5 years there as well. So that's it for the kind of my journey portion. And I can definitely entertain questions after. We can, if you want to ask specific questions, that's fine. So as I mentioned at the beginning of my talk, I did my postdoc. So after I finished my PhD program, I went on and did a postdoc at NASA. And as I'm an organic chemist, I actually got into this field which is called astrobiology, which is the title of my talk. I call these the 3 NOVA TV show questions. When you watch any NOVA science questions, they always are science programs, they always start off, how does life begin and evolve? Does life exist elsewhere in the universe? What is the future of life on Earth and beyond? That's kind of how it starts off. And that's exactly what astrobiology is dominated. It's a discipline that's dominated by these 3 big questions. Almost you can't even begin to understand how can science even attack these types of problems. But in fact, this is what the field is, these big questions. And what's interesting about this and why I like the field of astrobiology is that it brings all fields of science together and engineering. As you can see there, you might find your major on there and probably many more. Astronomy. But why astrobiology? Well, I mentioned that I was interested in biology when I first started because one thing that fascinated me was I was always interested in this question as to how did life start on Earth and what is the origin of life? Maybe I didn't reframe that question, but I always was curious about where did we come from and why is it that there's only one place that we know of where life exists. And as I got into biology classes and I started finding out some information, the key concept that got me to thinking about chemistry was that life is based on this field of chemistry called organic chemistry. And then I thought, wow, this is something that this is a way that I can use my major and start maybe approaching this problem. And I know that maybe not everybody has taken organic chemistry, so I thought I'd put up a little fun periodic table here and ask you, what is organic chemistry? Does anybody know? I'm sure a lot of you do, but any volunteers? When someone says organic, what does that mean? Yeah. You can go out and find it, yeah, but how about scientific? What's the science definition of organic chemistry? So you're close. Okay, how about you?
Chemistry primarily focused on carbon compounds?
Yeah. Whenever you hear the word organic chemistry, don't think it's pesticides-free chemistry or anything like that. It's grown organically. It's carbon chemistry, okay? Now here's the thing, carbon can't do it by itself. And when we talk about biological organic chemistry, like what you were saying in terms of things that are living, there are actually 5 other elements. So organic chemists really use 6 elements. And you could probably take a moment and guess in your head what are the other 5 elements, and then I'll put them up. Predict in your head what you think they might be. Think about your biology class. There's always 1 or 2 that you forget. So here they are. It's carbon, hydrogen, oxygen, nitrogen. Last 2 are a little bit harder. Start thinking about DNA. Phosphorus. And the last one, if you think about proteins, sulfur. These are called the biogenic elements. So when we talk about the organic compounds in life, now synthetic organic chemistry or polymer chemistry that uses organic chemistry uses many other elements. But when we're talking about life uses these 6 major elements. It's all based on carbon, but carbon doesn't do it by itself. And so this is organic chemistry, so whenever you think about that. So when you go into organic chemistry, you'll be introduced to this, these 6 elements and in all sorts of ways and how they come together. Okay, so that's organic molecules. But the origin of life, when we talk about life is based on organic chemistry, it really is a question. It can be broken down into many different ways, but one of the major fundamental questions is, how did those first organic molecules appear on the early Earth. We have an idea that Earth is about 4.5 billion years, diversification of extant life from the last universal common ancestors, about 3.6 billion years. But there's this huge period of time, a billion years, we don't know anything about. One thing that we do know, though, is that there had to have been a period of time what's called prebiotic chemistry, where organic molecules were either being generated or whatever fashion, but coming together to form something a little more complex, but before the emergence of life. And this is a field called prebiotic chemistry. It was not a field for many, many years in the early 20th century. In fact, it wasn't even considered within the realm of science. If you said you wanted to study prebiotic chemistry, you were not considered a scientist. It was, however, turned into the birth of prebiotic chemistry as the science came in about 1953. 1953 was actually quite the year, not only with this experiment, but there was another experiment, or another paper that came out, but I'll talk about that in a second after this. The Miller-Urey experiment really changed the field of prebiotic chemistry into a science. Harold Urey was a Nobel laureate by this time at the University of Chicago, and Stanley Miller was his early graduate student. And Stanley Miller was looking for a new project, or looking for something to do, and he approached Harold Urey and said, your ideas about how prebiotic molecules could have formed, or how the first organic molecules on the Earth could have formed, interest me, and I want to test them out. And Harold Urey supposedly said, no, it's not good for a graduate student, this is pseudoscience, these are just ideas. Well, Stanley Miller convinced Harold Urey that, in fact, they should try it out. And what they decided to do is say, well, let's actually predict or set up a model Earth. And this is the apparatus. And actually, if you have a high school biology book, in your room somewhere, at home, open it up. They actually have this in there. They actually show the Miller-Urey experiment even in high school biology books. I'm happy to see that. But what they did is they said, well, here is, and I'll come over here and point because my laser pointer is not working. This represents the oceans. And just like today, the oceans evaporate. So water vapor leaves the oceans and goes into the atmosphere. Well, in this experiment, they had to simulate an atmosphere and keep it closed off to the real atmosphere on Earth at the time in 1953. So they enclosed it in this bowl where they evacuated, and they only put in specific gases. The gases they put in were, water vapor is one, ammonia. They figured, well, there's probably ammonia, it's a very primordial gas, hydrogen, and then the carbon source was methane. Methane's a very simple organic molecule. And then they said, well, we need an energy source. What could have occurred on the early Earth? Well, lightning. Lightning could have occurred, and lightning did occur, so most likely, maybe that was your way. So what they did is they did a spark discharge experiment to mix these gases, very simple gases, and see what happens. And then what's interesting is that this part of the apparatus is raining out of the atmosphere. So as rain comes out, it drains back into the ocean. So simulating kind of this water cycle with its atmosphere. So they did this and did what's called the spark discharge experiment. And after a few days, it wasn't clear anymore. In fact, they found a lot of gunk coming down. And so you can see this is the atmosphere, and it's just raining out, and all this brown gunk coming down into the oceans and recycling up to the top again. This was interesting. They found, in fact, that there were amino acids produced. And this shocked the community because first they thought, well, it's contamination, but no, after they published their paper, people began to believe that, wow, this is something that you can actually start testing. They have a model atmosphere, and they did that, and this got a lot of press. Well, since then, the prebiotic chemistry has become more advanced and more sophisticated than just this, but this started it, that you can maybe start studying, having a model of what the early Earth was like, okay? And so I had a question or a comment. 1953 was actually also important because this was when the structure of DNA was proposed. And it's funny, that one supposedly didn't get as much attention as this did, but in fact, that really progressed science even farther. Once the structure of DNA by Watson and Crick was proposed, then the entire, this golden era of the molecular biology, golden era was kind of just took off, and biology was forever changed. But this also was born during that year as well. This is a bit harder because it's a lot of ideas and models that have to be tested. Okay, even though there have been many models of prebiotic chemistry put forward, there is still the main question that always bothers people. How do you know that what you're doing in the lab, what you're making in the lab, as a model, really occurred? You don't know. There's no way, you can't go back in time and see how the early Earth, what the early Earth looked like, what the composition was. There's definitely ways you can approximate looking at maybe geology, geochemistry, but there isn't in terms of the prebiotic chemistry. And this enters in the topic of my talk here. So here you have on the left is this model atmosphere, model prebiotic Earth, and this is maybe what actually occurred. Well, we don't know, but we do know what type of chemistry was occurring at 4.6 billion years ago. And this is why I bring up the carbonaceous chondrites. Meteorites that come to Earth, and so actually here is, a few years ago in 2012, up here in Northern California, the Sutter's Mill meteorite is one such carbonaceous chondrite that streaked across the sky and people took pictures of it. But these are a special class of meteorites that contain organic compounds. And I know the word carbonaceous implies they're just oozing of organic molecules, but it's not. It's about 0.3 to 3.6 weight% of carbon, containing carbon, soluble. And these rocks are primitive in composition, and they're mostly unaltered material from the early solar system. What I thought I would do was kind of throw up a little timeline of what meteorites, or why they are so ancient, and how is it that we know this. To do that, we have to go to even before the solar system was formed. I mean, these are models of what we think where meteorites come from. First of all, organic molecules are not just produced in meteorites. In fact, astronomers tell us, do we have any astronomers in the astronomy majors? No? We have physics, so that's close enough. Physics and astronomy is very closely related. But if you like astronomy, this is definitely an area that could benefit even more. People that are astronomers, not looking just at stars, but also looking into interstellar space, looking at the spectra of organic compounds that are out there, even now. Our solar system was born out of a nebular cloud, and these are called these protosolar systems born out of nebular clouds, and astronomers show us that these organic molecules are already present out there in interstellar space. So we have no reason to think that they wouldn't have happened in this area. And we even have research, even at Ames, there are people at Ames that are looking and simulating interstellar grains and actually doing chemistry with high energy radiation. So already, even before our solar system formed, there's organic chemistry being produced. Well, as the solar system formed, mass accretionary model, not everything became planets or the sun. The asteroid belt in between Mars and Jupiter is material. This is material that is primitive material from the early solar system. They didn't become planets. Well, on these asteroid parent bodies, there are chemical reactions that are occurring that continue to occur. And it's facilitated by this, what we call aqueous alteration, micro amounts of water that also help contribute to organic synthetic processes. And this contributes to that. So these asteroids are floating around, there's more organic reactions going on. But every so often, pieces break into each other and fly off and fly out of the asteroid belt and start entering into the gravitational pull of planets, nearby planets. And that's how these meteorites actually come into these planets. Well, there's a special class of these rocks called carbonaceous chondrites that are fragments of this material, and they preserve these organic compounds. And by the way, I have a little piece of that here, which you can take a look at later. These travel to places like the Earth, and they're very rare. We get a lot of meteorites, but we don't always get a lot of carbonaceous chondrites. They're very rare, but they do travel to planets like the Earth. And they impact the Earth, and hopefully scientists are there to gather them up and study them. And one of the most famous ones, again, I have a piece of crushed up powder of it here from our lab. It's on loan from Ames, is the Murchison meteorite. And this was, it's called the Murchison meteorite because it was an observed fall. It actually was seen to fall in the town of Murchison, Australia in 1969. And this was during NASA's moon mission days, and so people were equipped to actually have this material and go out and look at it and store it safely and protect it from further contamination. So that's kind of the timeline of, or the chronology of why meteorites are records of this early solar system. Okay, if you're taking organic chemistry now, you probably recognize these functional groups. If you aren't taking the organic chemistry now, that's okay. What I'm trying to show you is that these meteorites contain just about all of the classes of molecules that you'll learn in your organic chemistry textbook. Aldehydes, ketones, esters, aromatics, everything that you can see. And I invite you after to come up here and smell some molecules. They're not from the meteorites, but one of them, you are going to recognize the smell. And one of them actually was found and detected in small amounts in one of the carbonaceous chondrites. So you can see this. Now these are all compounds that you've smelled. They're all safe. You can buy them online. They're all flavorings. But surprisingly, one of them actually was also found in a carbonaceous chondrite. It's not surprising, but maybe to you it might be in the beginning. Like, oh, how, but it is. So all of these organic compounds, classes of organics are found in meteorites. Well, the Murchison, as I mentioned, is particularly well studied because it's quite diverse and it has a large amount of all sorts of different molecules in meteorites. I mean, as it's been detected. This is not for you to take notes, it's just to show you that this is an ongoing tabulation of the types of classes of compounds found. Why it's important for us, well, I'll tell that in a second because I think this is an important question. I guess the question is, how do we know, really? And as you go on through science, you should always, especially when you go into research, you should always be asking yourself, am I deluding myself? Is this really coming from space? Or is it just contamination? Because anything that enters the Earth's atmosphere and it hits the ground is going to be contaminated. And here's a little quote here. What appears to be the pitter-patter of heavenly feet is probably instead the print of an earthly thumb. And of course what they're saying is that, oh yeah, you think you're seeing something made up in an extraterrestrial environment, but probably not. Maybe somebody here was just holding it with their fingers. They should be slapped. And they have contaminated. You have bacteria on it. I mean, as soon as it touches the Earth, there's contamination on the shell. So how do you really know that what you're looking at is extraterrestrial and not terrestrial contamination? The best approach, and the first approach, is you always assume some level of contamination. Always. In fact, that's every meteorite. I mean, it's anything that comes to Earth, it's going to be contaminated. But how do you sift through what's contamination and what's not? Well, we have standards and ways to detect it. We have a list of approaches. The first, probably what's, I guess, the gold standard is that what we find is that you get enrichments of isotopes in extraterrestrial organic molecules compared to these terrestrial counterparts. So if you remember from your chemistry, so carbon-12, 6 neutrons, 6 protons. Well, there's also other isotopes of carbon. We have just one other neutron, so carbon-13 has one other, so 7. And then, of course, carbon-14, which is radioactive, has 8. But carbon-13, you see enrichments of carbon-13 and deuterium, so heavy hydrogen, in extraterrestrial samples. And this is due to isotopic fractionation that occurs in cold interstellar environments, even on the meteoric parent bodies. Different than here on Earth, life also selects out the lighter isotopes. So you get a certain isotopic signature on Earth already, but then also in space, you don't get that selectivity, and you get other types of separation processes, which are called isotopic fractionation. So that's the gold standard, but there's many other ways, and here's some other ones. Here on Earth, the biological molecules, if it really were contamination, you actually will see select peaks of certain classes of organic compounds that represent what you find in biology. But yet in meteorites, when you look at the classes of organic compounds, you see everything. You see, if you take organic chemistry, it'd be like as if you threw something in the lab and let the reaction go. You just get a slew of stuff. Biology uses enzymes to selectively create just certain parts of an organic or one class or one particular molecule of a class of organic molecules. But in what is called an abiotic environment, you get high structural diversity. You get every isomer possible. That's another clue. If you don't get that, if you start to see only select isomers, then you got a problem. You probably have some contamination going on. Also, and this is an organic chemistry term, you get what is called racemic mixtures. How many people are taking organic chemistry? I'm not going to ask you a question, I'm just curious. Is anybody taking organic chemistry? Okay, I'm not going to put you on the spot. When you do this, life uses one version, a hand. You have a right hand, you have a left hand. Let me put mine. And they look the same, but as you know, they are mirror images of each other. Many things, but you can't superimpose them on each other. This is the same thing happens with a lot of organic molecules. Carbon compounds have 4 different groups. You get mirror images. They're called enantiomers. In biology, you get a selection of one enantiomer over the other, a right-hand or left-handed version. In meteorites, just like as you were in the lab, if you're just to do an abiotic approach, you actually get the production of both hands. And that's expected. You would expect that. And so if you see racemic mixtures in meteorites, that's a good sign. If you see more of one hand version versus the other, then most likely you might have an issue of contamination. And it's clear, L amino acids versus D amino acids. If you see L and D together, that's one thing. If you see an enrichment of one hand, then you know you probably got some contamination. So that's another thing. And then, most importantly, is that you typically see a decline in abundance with increasing carbon number. And what that means is that you get higher amounts of small molecules. And as you build up larger and larger and larger species, that takes more energy, takes more time, prolonged effects, and so that is actually, you go from high amounts to low amounts of these larger molecular weight species. In biology, you actually will get large amounts of high abundant molecules, such as large fatty acids. And so if you see this typical decline in abundance, then you know you're probably looking at something that's extraterrestrial. If you start to see spikes now of these larger molecular weight compounds, then potentially you have some contamination, and you got to figure out what's contamination and what's not. So these are the 4 general rules that people look for when you're looking at organic compounds in meteorites. So ways to help differentiate between terrestrial and extraterrestrial. Okay, good. So now let's actually talk about why we're so interested in them. Well, here on the left, life uses proteins, nucleic acids, carbohydrates, lipids, and it uses metabolism. All of those large compounds are based on building blocks, such as amino acids for proteins, nucleobases, and sugars for nucleic acids, sugar derivatives, sugars for carbohydrates, and fatty acids, and glycerol for lipids. In meteorites, we don't find these large molecules, as I just mentioned, but we do see classes of all of the building blocks of life in meteorites. But we don't just see the amino acids that are found in life. We see many more. Nucleobases, adenine, guanine, thymine, cytosine. We see those, but we also see many more nucleobases, stuff that they're not found on Earth. Carbohydrates, sugar derivatives, and of course we see a lot of fatty acids, all sorts of types. Glycerol, tons of glycerol. What we're interested in our lab is the metabolites. And now I can move in the last few bits of my talk as to what we are specifically interested in. But what I thought I would share with you is what is it that we do in our lab on a daily basis? What is the process of science that we take in our lab? And I thought I'd put this up here just to show you the tools of investigation. And I broke it down into 4 parts. There's the analysis of meteorites, reading of scientific literature, the tools of analytical chemistry, and the tools of organic chemistry. First and foremost is the meteorites provide the clues. They give us the clues to this ancient chemistry. And a big part of what we have to do is use analytical methods to identify these compounds. What we find is, I'll mention on the second slide, is that gives us the ideas, oh man, there's a new molecule here that this is surprising that it's here. Well, the first thing you do, you start reading the literature. I put up astrobiology just because it's an astrobiology themed talk, but we don't just read the Journal of Astrobiology. We read chemistry journals, everything. But reading of the literature is just as important. This is something that you probably don't think about so much when you're studying, but when you go into the lab, reading of the literature really follows this. A day in the library, say, is a month in the lab. Of course, nowadays the library can be your desktop, or your laptop. But this is true. Reading is a constant process. And it helps plan experiments to figure out, well, what is it that we're looking at? Well, the next thing we do is, after you read the scientific literature, we start, and figuring out some of these questions, we start testing out our hypotheses. Well, if this is being formed in this way, maybe this is a precursor. So we use analytical instrumentation, gas chromatography, mass spectrometry, liquid chromatography, mass spectrometry. These are ways to separate out molecules, identify molecules. If you've seen CSI shows, they just put it in the machine and out pops the structure and out pops, the name. And it's not always that simple, but it's the general principle where you can identify compounds. And then we use NMR, nuclear magnetic resonance. Often though, the stuff that we see in these meteorites, you can't buy. You can't buy these standards. And this is where I come in a lot, where I came over to Ames, is that you also have to make molecules. And that's why having organic chemistry is important. So the tools of organic chemistry, where we can test some of these hypotheses, where we actually make it, we synthesize these molecules, not available at the store. And that's Joe Salveson, a student at UC Santa Cruz, doing some synthetic chemistry. And the master on the top doing the analysis. So this is kind of, in our lab, this is the four kind of pillars of what we do. Every lab's different. They have, they have their own process, but I can guarantee every lab reads the scientific literature all the time. In fact, I cannot tell you how many times where we have had our aha moments when you just read something from a completely different field, but it is relevant to what you're doing. So reading is absolutely important. So I talked about metabolic molecules. Before I got to Ames, I was a graduate student. George Cooper, who I told you was my boss, or is my boss, was already doing work, has been doing work on meteorites for many years. He's a world expert in meteorites. He actually published this paper in the Proceedings of the National Academy of Sciences in 2011 that just captured my attention, and I said, I gotta work with this guy. He's doing some really neat stuff. He found, in these meteorites, he published a paper where he found a molecule called pyruvate, citrate, isocitrate, oxaloacetate. These are all compounds in a core part of our biological metabolism called the citric acid cycle. This really surprised me because some of these molecules are very fragile and they should not have persisted in these 4.6 billion year old pieces of rock. But let me explain why they're so important to life. I tried to make the picture look nice, but I know it's still a little bit complicated. Probably even when you took biology in high school, many years, or even now, you've learned about glycolysis, cellular respiration, and it leads into the citric acid cycle. This molecule called pyruvate, which I have a structure up here for those of you who are taking organic chemistry. Pyruvate is really a central key small molecule in metabolism, which the process for generating cellular energy, but also for process of generating molecules. How is your DNA made? Well, it's made because the building blocks of it are being produced from these metabolic processes, most notably the citric acid cycle. Pyruvate is produced from glycolysis. Your body takes sugars and breaks it down into pyruvate. And pyruvate is a small molecule that funnels into the citric acid cycle to generate many other biological molecules, but also to generate sugars for gluconeogenesis, other amino acids, everything. Pyruvate is a central role in metabolism. And what's interesting is that pyruvate is related to the citric acid cycle. It feeds into it. And so, by finding pyruvate and many of the molecules in the citric acid cycle, again, the structure is just shown for people that might want to, practice their recognition. This was very surprising, and this was a source this was a meteoritic source of pyruvate. Now, what has gone on since then is that we've come to find out that pyruvate itself could be a source for the production of many of these organic molecules that are associated with each other in metabolism. And this is what we are actually working on right now, is now that we've identified these organic compounds in meteorites, and we've identified that pyruvate itself might be the source for some of these, as in an abiotic sense, not in a biological sense. We think that the clues to pyruvate's role in metabolism, because it can by itself produce it without the action of enzymes, we think that maybe that might have given us a clue, these meteorites might have given us a clue as to why pyruvate serves its specific role in metabolism now by going to and leading into the citric acid cycle. Again, this is a hypothesis that we're working on, and we're doing these very specific studies. Okay, just about done. This pyruvate was found in meteorites. That means it's been in the solar system. It means that there's more than just one source of pyruvate from this one carbonaceous chondrite. And the question is, in terms of astrobiology, if we're thinking about life on other planets, life in other worlds, does this mean that maybe if life were found, would it be based on pyruvate as well, just because it's based on it's used in life here? And then the idea is, not necessarily. The origin and evolution of life was unique to Earth, while the organic molecules are ubiquitous in the solar system and even beyond. Each planet, each spot has its own evolutionary history, its own chemical history, and it could be that it's related, but it just the best scenario would be that don't assume it, but you can continue to explore it. And so if you're looking for life, you don't necessarily have to look for pyruvate-based life or DNA-based life, but look for the types of molecules that classify or that work in the same type of general way. And so that's kind of the big picture in terms of the idea of this in the context of astrobiology. Okay, what I want to do is the last two slides is tell you about some opportunities for you. I mentioned at the beginning of my talk that you should start exploring job shadows or internships. And the organization that I work for, the Blue Marble Space, which is my contracting agency, every summer they have a young scientist program where you can work online with the scientist, or actually at Ames we have an in-house young scientist program that is in the labs. And if you're interested in these, checking it out, and if you're interested in these topics of astrobiology, not necessarily the stuff that we're doing, it's a huge field, check that out. That's one. That's a very select one, and that's geared towards undergraduates. The next one is, I took from one of my students' slides that she put together when she was doing some outreach with me. But NASA has a NASA-wide, not just Ames, but also at JPL, Goddard, all over, this one-stop shop shopping initiative where you can actually look at opportunities all across these centers. And there are many types of opportunities. You can work in the summer for 10 weeks, full-time during the year, so if you live close by, you can go to Ames and work a few days during the week. And then of course we have semester appointments too. And these are all internships. And whatever level you're at, you can probably find a lab or find a position that might interest you. And again, it's everything that ranges from engineering, biology, space biology. We've got all sorts of stuff. And summer at Ames, definitely it's quite the it's well represented. So those are two opportunities that I want to bring that up. And I think this white slide means I'm done. So thank you. Any questions?
Well, thank you, Dr. Rios. Like you said, come up and lick the meteorite. Yeah, you know, you can sniff this stuff. So real quick on the checkout system, you guys had questions. So this is how it's going to work. We have a scanner on this side, a scanner on that side. Wait, don't run. Hold up. Pull out your ID card and we scan it. Also, make sure that you fill out the survey, because if you want class credit, it's going to be done on the survey. So if you have an iPhone, like I said, take a picture with your iPhone, it'll automatically take you to the survey. If you have an Android, you can take a picture and use a tiny URL. So you got a scanner on that side, a scanner on that side, and take the rest of the food that's left over. to turn this off.